Okay, the final gas law presentation here. We're going to talk about the ideal gas law, which really rakes together all of our gas laws into one overarching law. And then we'll talk about Dalton's law of partial pressure. So you may have heard the ideal gas law before. So PV equals nRT is the way this goes. So the pressure times the volume is equal to the number of moles times constant R here times the temperature. And R is just a completely empirically derived quantity. It is one that holds very true. And to 3 sig figs, it's 0.0821 with units of atmospheres, liters over moles, and Kelvin. There are other ways to tabulate that value in milliliters and torr and moles and Kelvin. But I always find it easier just to have one value and change any of the collected data to reflect the units that are in that gas constant. So if I have 1 mole of gas at 273 Kelvin and 1 atmosphere of pressure, by the way, if I'm at 273 Kelvin and 1 atmosphere of pressure, we call that standard temperature and pressure, or sometimes we just call it STP. So if you ever see STP in one of the problems, it's not like an 80s rock band or a fuel additive. It's standard temperature and pressure. So when I plug into that, I've got 1 atmosphere times the volume is equal to 1 mole times 0.0821 atmospheres, liters over moles, Kelvin, and 273 Kelvin. So I want to get V all by itself, so I'm going to divide both sides by 1 atmosphere, and I get a volume of 22.4 liters. So you might recall that I used 22.4 liters in the Avogadro's law presentation. So it just so happens that this is kind of a magic volume, that 1 liter of any gas at standard temperature and pressure is going to occupy 22.4 liters. So we call that the molar volume of a gas, and sometimes we just, rather than just leaving it as just liters, we'll write 22.4 liters per mole. So it's a good number to know. We'll put it to work, even do a little bit of stoichiometry with that problem, or with that value. So if you hadn't thought of it up to this point, anytime we have these stacked units like liters per mole, your antenna ought to tingle when you see that, because that allows you to go back and forth between the units of liters and moles. So we've got a conversion factor here, so let's put it to work. So let's talk about fun with molar volume here. So if I've got 0.255 moles of hydrogen at STP, so standard temperature and pressure, I want to know what the volume is. So I start out with the quantity that I measured, and I want moles on the bottom because I want to get rid of moles and I want liters. So the 22.4 liters goes on the top, the mole goes on the bottom. So this looks like it corresponds to 5.71 liters. And likewise, and I got way too excited and hit the button ahead of time here. So I've got 307 liters of oxygen, and I want to figure out how many moles I have. So if I use my molar volume and arrange the units so they cancel accordingly to give me moles, it appears that I have 13.7 moles of oxygen if I have 307 liters. So let's talk about more fun with molar volume. So as I mentioned, we can do stoichiometry with this. So I need to prepare 25 liters of nitrogen monoxide at STP, and I'm going to do this by reacting combusting basically ammonia with oxygen. This is an interesting reaction. I think it was proposed a couple of years ago. I don't know where it's went to, as alternative fuel for vehicles. So you could use compressed ammonia and oxygen from the air to run your car potentially. So if you have spare moments, you could look that up and see what became of that as a proposed alternative fuel. But anyways, I want to make 25 liters of this nitrogen monoxide for some reason. So I'm going to plug that in. And notice I've set this up just like our old stoichiometry table, but the difference is I've got liters per mole as my conversion factor. So I've got liters per mole, moles, and then I've got my coefficient, and then I've got my magic number at the bottom. So if I've got 22.4 liters per mole, if I divide by 22.4 liters, I'm going to get moles. I got 1.12 moles. My coefficient is 4. Dividing by 4, I get 0.28. So I can transfer that magic number over to my reactants, plug in their coefficients, multiply up. I get 1.12 and 1.4 moles. It shouldn't be surprising that the ammonia was the same number of moles because the coefficients are the same. Remember that Avogadro had something to say about that, the ratios of the moles and the volumes should be the same. So I'm expecting to need 25 liters of the ammonia. So let's just check that out. So if I multiply up, I get 25 liters of ammonia and 31.4 liters of oxygen needed to produce my 25 liters of nitrogen monoxide. Okay, one more thing we can do is to look at the density of a gas. So you remember that density was mass over volume. So we can look at density as molar mass over molar volume. And for methane, if I add up 1 carbon and 4 hydrogens, I get 16.04 grams per mole. And if I divide by the molar volume, I get 0.716 grams per liter. So I might want to know what would happen to some methane if I just let it go in the lab. Where would it end up in the room? So I might want to compare it to the density of air. So I know the value of the density of dry air at STP is 1.29 grams per liter. I know we're not at STP in the lab, but the density probably doesn't change a great deal from that. So it's somewhere around 1.29 grams per liter. So the methane should float in air, so it should rise in the room, and we'll find it near the ceiling. Just like anything that's less dense than water will float in water, the methane gas likewise should float in air. Okay, Dalton's law of partial pressures isn't that difficult to understand, so I've got an imaginary balloon here that I've pumped up to a grand total of 1 atmospheric pressure. And to do that, I needed to put in 1 mole of hydrogen, 2 moles of oxygen, and 1 mole of nitrogen. So I might want to consider what fraction of pressure is exerted by the hydrogen. And if you look at this, I've got a grand total of 4 particles, and hydrogen is 1 out of 4 of the particles. So it just makes sense that the fraction of the pressure exerted is 0.25, or a quarter. Oxygen is half of the particles, so it makes sense that half of the pressure is exerted by oxygen. And likewise, nitrogen is a quarter of the particles, so again, a quarter of the pressure is exerted by nitrogen. So I might want to know exactly what the pressure is, so I can take the fraction times the total pressure to get the pressure exerted, so 0.25 atmospheres in this case. So I took my fraction times the total pressure. And again for oxygen, and again for nitrogen. And one thing that Dalton also noticed, aside from the fractions times the total pressure giving us the pressure, was that the sum of the pressures added up to the total pressure. So it doesn't seem like earth-shattering work, but just dawned on him one time a couple hundred years ago. So the total pressure is equal to the sum of the individual pressures. Doesn't seem that exciting, but we'll make use of it in lab, particularly if we're collecting a gas, and sometimes we do that by having a chemical reaction going on in a stoppered test tube, and we've got a hose running from that test tube up through a pan of water and underneath a piece of glassware that has been filled with water. So as the reaction runs, it displaces the water and the container fills with that gas. So I might want to know, for instance, that if I've got a gas that I've collected over water at 25 degrees Celsius and the atmospheric pressure is 741.2 millimeters of mercury, I might want to know what the pressure of the gas is alone. So as the gas bubbled through the water, it carries some of the water vapor up in with the gas. So the total pressure actually reflects the pressure of the gas plus the vapor pressure of the water. And we're going to assume here that the total pressure is pretty close to the atmospheric pressure because it's balanced here. You can look up the value of the vapor pressure of water in tables, or I found lately that if I'm interested in a particular vapor pressure, I just type in the vapor pressure of water at 25 degrees Celsius and put that in Google, and lo and behold, I get a number. So I've got 23.8 millimeters of mercury, apparently corresponds to the vapor pressure of water at 25 degrees Celsius. So I know the total pressure was 741 millimeters of mercury. I don't know what the pressure of the gas is yet, but I know the vapor pressure is 23.8. So just by simple subtraction, I get the pressure of the gas as 717.4 millimeters of mercury.